All right, so here we go for our third foray into the land of electrochemistry. And as it says here, we are going to be looking at some free energy, some equilibrium and electrochemistry all together. So, free energy, if you remember what the deal with Gibbs free energy is, it tells you whether or not a reaction is going to be spontaneous. And if you noticed in one of the earlier videos, I said galvanic cells rely on a spontaneous redox reaction to make them go. So it should probably come as no surprise that we're going to be talking about Gibbs free energy and galvanic cells together, right? And so this galvanic or voltaic cell, they take advantage of spontaneous reactions to move the electrons. So we can relate Gibbs free energy to the cell as it also deals with spontaneous reactions, right? And so here is the equation that relates these two things, where Gibbs free energy is equal to minus the moles of electrons moving times Faraday's constant times the standard cell potential. Right? And Faraday's constant, for those of you who don't have it memorized, is 96,485 coulombs per mole, or joules per volt mole, which is always a good unit, and N, the number of moles of electrons transferred in a balanced redox reaction. And so I'm going to throw this little note in here, which is good to note. It's not explicitly stated often in the Faraday's constant units, but the mole in there refers to 1 mole of electrons, right? So just remember that in Faraday's constant, the mole refers to a mole of electrons that are moving. Okay, so of course, since we have an equation, we're going to do some calculating, right? So calculate the Gibbs free energy for the following redox reaction. And here we have a redox reaction involving silver and oxygen. And it has already been balanced as a redox reaction. As you can tell, we've got our water and our hydrogen in there, so it's been balanced in acidic conditions. We're going to split this up into our reduction and our oxidation equations here, where oxygen is being reduced, right, from 0 to -2. From its oxidation state, right? Because if we look, we've got 0 here and a -2 state here, while silver is being oxidized, right, from 0 here to +1 here. All right, so now that we have that out of the way, we can calculate our standard cell potential for this, because we know which one's going to be at the cathode and which one's going to be at the anode. So you remember that reduction takes place at the cathode, oxidation at the anode. So we can look up the standard reduction potentials on a chart for each of these, and we end up with this as our equation. And we know that E cell is going to be equal to 0.43 volts. So now, if you remember the equation from the last slide, we have Gibbs free energy equal to the number of moles times number of moles of electrons times Faraday's constant times the standard cell potential. We're going to put all those numbers in, right, because we can tell from our balanced equation that we have 4 moles of electrons moving, Faraday's constant, which is a constant, and the standard cell potential that we just calculated. And when we do all that, we have a Gibbs free energy of -1.7 times 10 to the 5th joules per mole, which, if you remember about Gibbs free energy, negative is going to tell you that this is a spontaneous process. And since galvanic cells use spontaneous processes to derive electrons, that makes sense that this would be a spontaneous process. Okay, so what we're going to get ready to tell you about here is that not only can we associate cell potential with Gibbs free energy, but we can also associate it with equilibrium. And we have a ton of equations here that I'm about to show you. So if you remember, this one that we just saw a minute ago relates Gibbs free energy to cell potential. And if you think back to some thermo lessons, Gibbs free energy is also related to the equilibrium constant. And when we put these two together, we get a lovely equation that equates cell potential to the equilibrium constant using the gas, ideal gas constant, temperature, moles of electrons, and Faraday's constant, all to the natural log of the equilibrium constant. Fantastic. Say, how could this possibly get any better? Well, by introducing the Nernst equation. That's how. Because in the Nernst equation, we relate the cell potential non-standard, right? Notice that it does not have the little circle. And Q, and if you remember from equilibrium, Q is the reaction quotient, and that is what we use when we have things under non-standard conditions, right? So Nernst equation looks at cell potential under non-standard conditions. And there are two more versions of the Nernst equation that you will run into, right? One here, where instead of natural log, we have just log, right? That's what this value does. That's compensating for changing natural log to log. And then because R and F are constants, and if you look at this at 298 Kelvin, right, or standard temperature, or standard room temperature in science, you can get rid of the RT and F, right? And this is specifically at 298 Kelvin, right? And so this becomes a pretty simple equation to use because there's no constants left in here, right? You have your moles of electrons moving, you have your concentrations under non-standard conditions, and you have your standard cell potential, all there, ready to go. Okay, so of course we're going to do some calculations surrounding this, and so we're going to calculate E, which is the non-standard cell potential for the following reaction at 298 Kelvin with the given concentrations. Now notice, right, it's at 298 Kelvin, so that's going to tell you that we are going to use a specific version of the Nernst equation for this calculation. So looking here, right, we have this equation that is very much like the one that we balanced a couple videos ago. So I'm not going to go through breaking this into our oxidation and reduction equations because you should have basically the same equation in your notes and be able to see how many electrons are moving and what is the reduction and oxidation half reactions for that. So if you have any questions about that, go back and look at your notes. But suffice it to say, we look up on our value tables with our two standard reduction potential values, and we find that the standard reduction or the standard value for the cell is 0.79 volts. From there, right, we are going to set ourselves up an equilibrium statement about this particular reaction where we look at our products over our reactants. And when we look at products over reactants, right, we look at all the things here that are not solids or liquids and all the things here that are not solids or liquids, right? And so our only product that is not a solid or liquid is our chromium ion, right? So that's the only thing on top. All the things in our reactants are not solids or liquids, so those go on the bottom. And luckily, we have values that are given to us to put in here. And so we put all our values in there, right? And we find that the reaction quotient is equal to 5 times 10 to the negative 11. Now, we're going to put both of these values into our Nernst equation, because it's fun to say. And it's going to look something like this, right? Where oops, I forgot to change this to 0.79 volts, right? So that should be 0.79 volts right there. And when you calculate all this out, right, and so here's our moles of electrons, right? Like I said, if you look back in your notes, you'll see that there are 6 moles of electrons moving in this equation. And when we do all this out, we find out that the cell potential under the non-standard conditions given is 0.89 volts. It's amazing. Okay, the last thing we're going to talk about here, unless I'm completely off on what comes after this, is concentration cells. And what a concentration cell is it is a voltaic cell that uses the oxidation and reduction of only one species, right? So up until now, right, the standard voltaic cells we've seen have used a different species at the cathode and anode, right? The ones that we looked at used zinc and copper. In a concentration cell, right, you would just use like copper and copper, right? But the two species would be at different concentrations, and that difference in concentration drives a spontaneous reaction that produces EMF, and everybody's happy, right? So why would we even care about doing this if these things tend to quench themselves and, things like that? It turns out that this process is very important for living things in that it helps with the operation of nerve cells in the brain, the regulation of things like heartbeat, and of course, the one that is definitely most important to us, the functioning of the pH meters that we have used in lab. So that is calculating some cell potential under non-standard conditions, and we'll just have one more video and then we are done with electrochemistry. I'll see you in class.